Hello all and welcome to Physics with Pranav. If you're new to my channel, I'm Pranav. I used to be a CAIE student in science and math. I've tutored GCSE and A-level students from around the world in physics, and I'm an IGCSE world topper in science from back in 2013. This video is part of a series for the CAIE IGCSE curriculum, where for each chapter of the curriculum, I explore the key concepts tested based on data from recent past papers. I dive deeper into the concepts so you have a solid foundation of them, and then I show you how to apply these concepts in solving past paper questions, which is what we'll be doing in this video. In particular, this video will look at questions from paper 4, which is the theory paper, and chapter 8, which is work done in power of the CAIE curriculum. If you are a GCSE student but are not studying the CAIE curriculum, don't worry because the concepts that are tested read across quite well to Edexcel, AQA, and OCR. There's a fair bit of an overlap. The methodology used to approach the questions will also serve useful irrespective of which curriculum you're studying in. So you'll still be getting essentially a lot of value by watching these videos. This video on chapter 8 is one of 3 videos I made for this chapter. If you want to check out the other 2 videos where I explore the key concepts tested, as well as how they're applied to paper 2, which is the multiple choice paper, please feel free to check the links in my description below. So let's take a look at some paper 4s for chapter 8, work done in power. The first paper we're going to be looking at is October-November 2023, and we're going to be looking at variant 4.2. So if I scroll down to find the first question on work done in power, we could see that this question here wants us to show the amount of work done, and it's part of a broader question. So we could see that the question is around the motion of a car, and there's a lot around kinematics to start with. And part C looks at work done. The key thing to keep in mind, as I always mention, is for paper 4, you're going to have an interplay of different concepts and different chapters in the same question. It's very common. In paper 2, you can expect questions to be from a single topic. There will be some overlap, but in paper 4, more often than not, you would have questions from a range of chapters within the same question, I suppose. So if we look at question C then, the car decelerates, so we've got a car, it decelerates from 13 meters per second to 0 meters per second at a constant deceleration. The mass of the car is 1,350 kilograms. The car travels 13 meters in 2 seconds as it decelerates. So show that the work done by the car as it decelerates is approximately 1.1 into 10 to the power 5 joules. So the first thing that I always start off with is to write out the formula for what you need to calculate, right? So you need to calculate work done. We know that work done is a product of force and distance. Yep. So do we know the force here? We don't. There is no Newton values that you can see, so we don't know the force. We'd have to calculate the force using some of the quantities that's given. Do we know the distance? That we do. We know that the car essentially travels a distance of 13 meters, so we know the distance. So we know a part of this equation, but we don't know the full thing. Now, in terms of what I'm given, if I want to calculate force, obviously there's a bunch of different formula, but the most common one is mass multiplied by acceleration. And I think the question hints at using that as well, because they talk about deceleration, they talk about mass. We know that force is mass times acceleration or mass times deceleration if it's a resisting force. So essentially, it'll be mass multiplied by the deceleration of the car. So in order to calculate the deceleration, we have to essentially calculate the value of the deceleration because we know the value of the mass, and we need essentially the change in velocity and the time over which it happens. So we know that for this car, it goes from 13 meters per second to 0 meters per second, and it does so in 2 seconds. So which is it's a fairly sharp deceleration. So the value would be around 6.5 meters per second square. That's the value of the deceleration. We've got the mass of the car, which means the mass of the car multiplied by the deceleration is going to give us the force. And then we know that work done is force multiplied by distance. So once we've calculated force, which is 8,775 newtons, if we multiply it by the distance over which the force acts, we get a value of 114,075 joules. So essentially, if we rounded that, that would give us a value of 1.1 into 10 to the power 5 joules. That's approximately that value. So that's why it's a 4-mark question. The reason it's a 4-mark question is because It requires you to calculate force, to calculate work done, and then to calculate force, you need to calculate acceleration. So it requires you to pull on a number of different concepts. So, acceleration is kinematics, then force is obviously from forces in motion, and then work done is from the topic that we are exploring right now. It requires you to essentially be able to utilize concepts and formulae from these different topics to be able to get your end answer, which is for work done. And the good thing about this question, I guess, is you know roughly what to expect. So you know if your answer is right pretty much immediately as you calculate through the different formulae. And essentially, if your answer is not matching that, then you know you've either assumed something incorrectly or you maybe used the wrong number. So I think I like these types of questions, these type of proof questions, because it tells you right away if your answers are right. So question D goes, on another day, the car in C travels a longer distance while it decelerates from 13 meters per second to 0 meters per second. Deceleration is constant. So essentially, this is from the topic of kinematics, so I know I've answered here, but it's not around work done and power. So I will not be covering this bit in this video. However, I have made videos on both the concepts of motion as well as forces in motion. And I've also applied these concepts to past paper questions. You can find links for playlists which have both the key concepts from different chapters as well as applying the key concepts to the past paper questions in my link below, in the description below. So please feel free to check it out. So if we move on to the next paper. So the next paper we're going to be looking at is October, November 2022, variant 4.2. So in this paper, we have looked at this paper when we were going through the concepts of energy. So when we were looking at that chapter, we did a couple of questions from this paper. I just want to revisit one of the questions that we looked at. So I'm not going to try and go through the whole concept of energy, because if you want to check that out, feel free to check out the playlist that I have on past paper questions, and go and check out paper 4, solving energy questions from CAIE paper 4. So if you look at that video, you will be able to see how I have applied concepts from that chapter to be able to solve questions. And again, like I said, you'll find that there's going to be quite a bit of an overlap between the energy chapters and this chapter on work done and power, so it is expected. But for now, I just wanted to revisit one of the questions that we did as part of that video, because I think it's really valuable and will be of use to you when you want to try and solve questions relating to power. I think it's a good question, so it's worth revisiting. So question 3, we look at essentially a water turbine system which uses the energy from waves, essentially the flow of water, to be able to generate energy. So part A and part B1 are related to energy sources and questions around that. We will look at part B2. So the mass of water passing through the turbine each second is 6 × 10⁻³ kilograms, essentially 6,000 kilograms. The speed of the water is 2 meters per second. Okay. 40% of the kinetic energy of the water is converted to electrical energy. Calculate the electrical power generated. So essentially you have kinetic energy for input, and then electrical energy is the output. So they're saying that 40% of the kinetic energy that is hitting, or essentially kinetic energy of water that is hitting the turbine blades, is being converted into electrical energy. So the first thing that we need to do then is we need to calculate the total amount of input kinetic energy. So we know that kinetic energy is half times mass multiplied by the square of the velocity. So we know the mass, we know the velocity. So if we multiply half times 6,000 times 2 squared, that gives us a value of 12,000 joules. So it's 12,000 joules of kinetic energy hitting the turbine blades of this system every second. And we know that only 40% of that kinetic energy is converted to electrical energy. So if you multiply the value of the kinetic energy by 40% or 0.4, we get electrical energy value of 4,800 joules. So when 12,000 joules of kinetic energy hits the turbine blades, we get around 4,800 joules of electrical energy. So that is the conversion. But we want the electrical power that's generated. So power, we know, is energy transferred over a period of time, what is the rate of energy transferred. So we know that 4,800 joules of energy is transferred, and we know that it's being transferred every second because they say that each second the turbine blade is hit by 6,000 kilograms of water. So that we have there is essentially it's value of power as well. It'll be 12,000 watts because we've got 6,000 kilogram of water hitting the turbine every second. So what you have here then is 4,800 joules of electrical energy every second, or 4,800 watts. So that is our answer there. So that's electrical output or electrical power that is generated by the system. So if we go around and look for any more questions that we have on these concepts, no, we don't. But yeah, I know we did this in the paper for chapter 6 and 7, which are the energy chapters, but I just wanted to revisit it because I think it's a good question. It requires you to apply the concepts of energy, it requires you to apply the concepts of efficiency, and then tie it back to the concepts of power, essentially. So I think it's a good question which combines a number of different concepts together, and that's why it's 4 marks as well. So move on to the next paper, which is May-June 2022, variant 4.3. Go down, try and find the first question on essentially work done and power. So water is held behind a dam in a hydroelectric power scheme. To state the main form of energy stored in the water behind the dam. Again, I know this question has or tests the concept of energy. And again, like I said, there's always going to be a bit of an overlap. So without avoiding to have to repeat myself, just assume that that is most likely going to be the case. So let's look at this question. So the main form of energy for the water stored behind the dam would be a gravitational potential energy, because usually the dam is at a height. The water is released, it usually flows down the dam, and then the gravitational potential energy is converted to kinetic energy of water, and the kinetic energy of water is then transferred to a turbine, and that is generally how dams make electricity. So that is gravitational potential energy. Question B, the water is released from the dam and falls a vertical height of 410 meters at a rate of 480 kilograms per second. So that's a mass flow rate. Typically, when they don't just give you mass, they give you like a flow rate, you know that there's going to be a question around power. So we've got calculate the rate at which energy is transferred by the falling water. So the energy transfer that's taking place is the gravitational potential energy transfer. So we need the formula for the gravitational potential energy, which is going to be the mass multiplied by the gravitational acceleration, or the gravitational field strength multiplied by the height difference. So we have a mass of 480 kilograms per second. We have G, because it's 2022, pre-2023 paper, we can assume a value of 10, and it's essentially falling a distance of 410 meters. Because we have mass flow rate, what we have is a rate of transfer of gravitational potential energy, which gives us a value of 1968000 joules, which is 1968 kilojoules. I must apologize here because there is an error with the units, because the rate of energy transfer is happening every second. The value should be 1968 kilowatts, not 1968 kilojoules, so that is an error from my end. Apologize for that. Just noticed that myself. And then if you look at part 2 of question B, the power scheme supplies a current of 270 amperes at a voltage of 6,000 volts. Calculate the efficiency of the power scheme. Now this is something that we haven't seen yet. So this was not covered in the chapter of energy. In fact, the concept of electrical power will be covered when we look at the chapters of electricity. But it is a question on efficiency, so I wanted us to have a look at it. Again, one thing that you will find is, apart from there being an overlap with the concepts of kinetic energy and potential energy, you will also sometimes get the concept of electrical energy, electrical power, and then you have to be able to use that to calculate efficiency, so that kind of question can appear as well. Although I haven't seen it as much in the 2023 papers, it's something that has shown up as recently as summer 2022. So it's probably worthwhile knowing. Again, when you do take up GCSE exams, you would have completed the topics of electricity, so you should know this equation for electrical power output, but I will just introduce it to you. So electrical power output is essentially the product of the voltage and the current. Yeah. So the voltage is the potential difference in an electric circuit. Again, it's something that we will look at in more detail. And the current is the amount of electricity that is flowing through the system. Yeah. So if we take the voltage, which is 6,000 volts, and we multiply it with the current, which is 270 amperes, we get a value of 162.0000 joules, yeah, of 1,620 kilojoules. Again, for the purposes of this question, you just need to remember that electrical power is voltage multiplied by current. I know we haven't covered this in our videos yet, but I will be creating a video on the concepts around electricity very soon. But yeah, for the time being, just this formula will suffice. So we have a value of 1620 kilojoules. The efficiency is going to be the useful output divided by the total input. So we know that the total input is 1968 kilojoules. That's the amount of gravitational potential energy that the water is transferring as it falls from the dam. And then the useful output that is coming out is 1620 kilojoules. Because both of them are in kilojoules, we can divide one by the other, and that gives us a value of 82.3%. So 0.823, you multiply that by 100, gives you 82.3%. So it's actually a very efficient system. You know, a lot of systems that you will see around you don't have such high efficiencies. They'll probably be around like 50% or less. And 50% efficiency, you'll be surprised to hear, is actually a pretty good value. So the fact that 82% of the input energy is being converted into output or useful output is very good. So then again, we've got a couple questions around hydroelectricity. So hydroelectricity is a renewable form of energy. State one disadvantage of hydroelectric power schemes. So the biggest disadvantage is the risk of flooding around the reservoirs. And state one other renewable source of energy. So you could state solar, wind, tidal, wave. there's a number of different ones, but solar is a fairly easy choice. So I'll just put that in there. Let me see if there's any other questions on work done or power or energy transferred. Not really, no. But yeah, that's an interesting question. Something just to be wary of, and again reinforces the point that in paper 4, in a single question, you'd be expected to integrate different concepts from different chapters together. So next paper we're looking at is May June 2022. We're going to be looking at variant 4.2. So the very first question here is a question on work done and power. So figure 1.1 shows an electrically powered bicycle. Okay, so that's the bicycle. When fully charged, the battery can deliver a power of 600 watts for 60 minutes. Okay, calculate the energy in joules stored in the battery when fully charged. Yeah, so the energy stored is going to be equal to the power multiplied by the time. You know, the power is work done or energy transferred divided by time. So if you rearrange the equation for work done or energy transferred, you know, to make that the subject, we would then get a formula of energy is equal to power multiplied by time. We know power is 600 watts, and we know that that is over a period of 60 minutes. We know that minutes is not the SI unit, so we'd have to use SI units, which is seconds. And we know that a minute has 60 seconds, so 60 times 60, and that gives us a value of 216.0000 joules, and that is what I put down here. So that is the energy in joules that the battery stores when it's fully charged. I state the form of energy stored by the battery. This is a classic question from the concept of energy stores and transfers. So batteries store energy in the form of chemical energy. Excuse me. It's important to remember here that yes, batteries are part of circuits, and usually the energy that they output is electrical energy, but the energy they store is chemical energy. So please don't try and get that wrong. I suppose it is easy to mix that up and get confused. So in B, we say the bicycle has a motor with an electrical input power of 250 watts. Calculate the time for which the battery can power the bicycle. So we know that the power is the energy transferred over a period of time. And then now we want to rearrange the equation because we want to know the amount of time for which the battery can power the bicycle. We know the amount of energy the battery has. So the time is going to be equal to the energy divided by the power. So we know the energy is 216.0000, and we know that it has a power of 600 watts. So we've been told that the bicycle has a motor with an electrical input power of 250 watts. My bad. So we're not looking at the 600 watts there. We're looking at the 250 watts here. So we're going to have this value of energy divided by that value of power to be able to give the time, which is essentially 8,640 seconds, which again, if you divide by 60, you get 144 minutes, which is around 2 hours and 24 minutes. So you could give it in hours and minutes. I've just given it in minutes because you have to express it in hours and minutes anyway at the end. So consider this bicycle compared to a small motorcycle. State 2 environmental benefits of the electrically powered bicycle. So obviously, if it's electrically powered, it won't have any emissions, which makes it eco-friendly, and the fact that it doesn't use any fossil fuels also makes it an environmentally friendly choice. So that is the question. I believe that's the only question on work done and power. So if we move on then to the last paper, which is October number 2020, variant 4.2. So again, if I go and find the question around work done and power, we got a nice 5-mark question here. So the kinetic energy of air passing through a wind turbine every minute is 720,000 joules. The electrical output of the turbine is 9 amperes at a potential difference of 240 watts. Calculate the efficiency of the wind turbine. So it appears like in a lot of the earlier paper questions, there is integration between the concepts of work done, power, and electrical energy. So it's just something to be wary of. So the first thing that we want to calculate is we want to calculate the input power. So we're given the input energy and we're given the time over which that input energy is transferred. So power is going to be equal to energy divided by time. We know the energy is 720,000. We know the time is every minute, which is 60 seconds. So that gives us a value of 12,000 watts. So that is our input power. If we look in terms of the output power, we know that we saw in the previous paper that the electrical power output is the product of the voltage and the current, or the potential difference and the current. So we know the potential difference is 240 volts. We know that the current is 9 amps or 9 amperes. And if we multiply that out, we get a value of 2160 watts. So that is the electrical power output, and that's the useful power output. So if we divide then, to find the efficiency, we have to divide the useful power output by the total power input, which would be 2160 divided by 12,000. Well, that gives me 0.18, which is 18%. So 0.18 by 100 multiplied by 100 gives me 18%. So that is the efficiency of this wind turbine, which is really low. 18% efficiency is really low. So a lot of the energy is lost either to heat or to sound. I know wind turbines can be quite loud when you're near them. So yeah, that's not a very efficient system. I don't think there are more questions on work done and power. Looks like there's a lot of questions around thermal concepts. So yeah, that's the last of the questions we'll be looking at in this video today. I hope you found this video useful. If you did, please like and subscribe. And if you believe someone else will also benefit from watching this video, please share this video with them. Thank you for your time, and I'll join you in my next video.